In section 2.5, we're going to be looking at what's called one-sided limits. And so you're really going to need to think almost like a plane landing. It's coming in on the runway from either the east or the west. And so that's kind of how I think about one-sided limits, as x approaching from the right or from the left. All right, so we're going to talk about that, and we're also going to talk about continuity. But let's talk about those one-sided limits. All right, we have some different kind of notation. So on these first graphs, we are asked to find the limit as x approaches a from the right-hand side. That's what that little plus sign means of f of x. Then we're asked to find the limit as x approaches a from the left-hand side. That's what the negative means. And then we're asked to find the limit as x approaches just a, which is what we did in the previous section. And so we have to look at the right and the left. All right, so on this problem, and then again, these are just copied out of the book from page 126, like problems 1 through 8. I think I copied the odd ones. All right, so on this graph, we're looking when a is equal to 2. So we're looking at that value. Well, as I'm coming in from the right-hand side, so that means a little bit bigger than 2. On the right-hand side, this is the part of the function I would touch. What is that value close to? It is close to 2. But if I come in from x on the left-hand side, meaning a little bit less than 2, I go up here to this part of the function, and what are we getting close to is 3. Now, when those two numbers are different, as in this case, and they ask you what is the limit as x approaches a, meaning from the right and the left, this limit does not exist. The only way it would exist is if these two numbers are the same. In fact, if we were to go look at our technique that we did from section 2.4, and I just would have asked you what is the limit as x approaches a, well, we could see, well, a little bit bigger than 2, we're here, a little bit less than 2, we're here. Those are not the same values, and that's why that limit does not exist. All right, let's look at this one. We have the limit as x approaches -1 from the right-hand side, and we want the limit as x approaches -1 from the left-hand side. All right, so again, the book has drawn us a little line at -1. Okay, so from the right-hand side, meaning to the right of -1, a little bit bigger than -1, where would we be? Well, we're exactly at 2. And if we go from the left-hand side, a little bit less than -1, we come way up here, and it looks like that would just keep going forever. And so positive infinity, or really that limit, does not exist. And so if I ask what is the limit as x approaches just -1, because these don't match, does not exist. Next one, we want the limit as x approaches 0 from the right-hand side. All right, so again, I look, here's 0. I want to go a little bit bigger than 0. What is my y value getting close to? 2. Then we have as x approaches 0 from the left-hand side, a little bit left of 0. And I'd have to come down here to this part of the function, and that's -2. And so if I ask you what is the limit as x approaches 0, does not exist, because again, those don't match. So you've got to really get used to that notation with the little pluses and little minuses to the right of the number. It's kind of really odd looking. All right, so again, we've got a is 1. So I want to go a little bit to the right of 1. I'd go up here. That's close to 2. To the left of 1, man, that's like right at 0. And I would say the limit as x approaches 1 does not exist. And I think they're giving you all of these examples about does not exist. I'm thinking at some point it would exist. Let's see if we can look at this graph. All right, let's see, what kind of problems could I ask you? Well, what if I ask you, what is the limit as x approaches 0 from the right-hand side? The limit as x approaches 0 from the left-hand side. And what is the limit as x just approaches 0? Okay, so same technique. Go to the right of 0, go to the left of 0, get really, really close. What does it look like the y value is getting closer to? Well, to me, that looks like it's close to 0. That looks like it's close to 0. So the limit must be 0. All right. Right. What if I ask you about the limit as x approaches 2 from the right or 2 from the left? Okay, so again, I'm going to go a little bit to the right of 2, go a little bit to the left of 2. Well, that y value looks the same. Looks like a 1 here, a 1 here. So again, I could say the limit as x approaches 2 is 1. Let me throw in another question. What is f of 2? When x is exactly 2, is y equal to 1? No, it hops up here and it equals to 2. So as you look at these pictures, think about left, right, things like that. And just to conclude, the limit as x approaches a single value, notice no plus, no minus, no right, no left, the limit exists if and only if the one from the right equals the one from the left. All right, so how do we do this if we don't have a graph? Well, pretty much just like we did in section 2.4, we're going to substitute the given value of x into the function. If we get that indeterminate form, then we're going to have to factor and reduce. All right, so just to kind of pick some problems, if I have the limit as x approaches 2 from the left, right? Now what they're trying to confuse you with that little minus sign is they're trying to make you think it's a -2, but it's not. It's a +2. So again, we're just going to put that value of x, that value in for x. So if I have 2 minus 3 over 2 plus 2, -1 over 4, and you're done. All right? Doesn't matter right or left. Let's look at another one. Let's say I have the limit as x approaches 3 from the right-hand side, and I have 4 times the square root of x minus 3. Now, you really couldn't have a limit as x approaches 3 from the left. Think about what kind of numbers are to the left of 3, like 2.9, 2.8. And if I plugged in like 2.9 or 2.8 in for x, and I subtracted 3, I'd get negative. Square root of a negative is imaginary. All right, so that wouldn't be good. But since I'm talking about 3 from the right-hand side, again, if I just plug in 3, I'm going to get 0, and that is fine. All right. Let's say I have the limit as x approaches 5 from the left, and I have x squared minus 25 over x minus 5. Well, let's see, if I just plug in my number, 5 squared minus 25 over 5 minus 5, I get 0 over 0, and that is that indeterminate form. So what can I do? Well, I can factor the top. Well, and the bottom is already factored. And I can reduce. And so then I can say, all right, the limit as x approaches 5 from the left of x plus 5. Again, just plugging in 5 for x, I get 10. Okay, so very much the same way, exactly the same way as we did the limits in section 2.4. The next thing we need to talk about is continuity. And you really, really, really need to know these 3 different conditions, right? Continuity, something continuous. Okay? The function has to be able to be defined at whatever a value you're talking about. The limit as x approaches a has to exist, and those two things have to be the same. Now that's a fancy way of saying that if a function is continuous at a point of the graph, so that the point is there is no holes, gaps, jumps, or breaks. In other words, could you draw the function without ever lifting your pen or pencil from the paper? And if you can, then it's continuous. If there's a jump, then it's discontinuous at that point. So for example, on number 39, and again this is in your book on page 127, all right, it asks us where is it discontinuous? And then state the conditions. Well, just look at number 39. There's a big jump from here to here, so there's no way that's continuous. All right, so where is that big jump? What does x equal to at that big jump? All right, so the function is discontinuous at x is equal to 0. You can definitely see when x is 0, we jump from up here to down here. Right. So what would be the conditions? Well, let's scroll back up here. Right. First of all, is f of a defined? Meaning, is f of 0? Does that exist? Well, yeah, you can come back up here and say when x is 0, if I plug in 0 here, 2 times 0 minus 4 is negative 4. So that condition works. But what about the limit as x approaches 0? Well, if you recall what we just talked about, if I go to the right of 0 and I go to the left of 0, I get two different values, and so that does not exist. So what conditions are violated? I would say condition number 2 is violated. Maybe I guess you could even say number 3 since the limit doesn't exist. Alright, so let's look at this one. Okay, are there any holes or jumps? Well, yes, there is. Again, right here, right there. And what is the value of x when that happens? Well, it just so happens, coincidentally, that it's discontinuous at x is equal to 0. All right, so if I look at the condition, condition 1 says, does f of 0 exist? Yes, it does. In fact, it's defined, or there's a point when x is 0, y is 2. But what about the limit? As x approaches 0, well, again, if I kind of go to the right and I go to the left, well, that does exist. I'm going to erase that and try to give you a little bit better picture of it. But if I go to the right of 0 and I go to the left of 0, I'm getting closer to 5, right? So that exists, but what's the third condition? That basically the first two answers have to be the same, and since 2 doesn't equal to 5, then the third condition is violated because the limit is not the same as the function, right? Other part, instead of just looking at pictures, they're going to say, where is this continuous or not? And this really goes back to the domain of a function. All right, so if you were to graph this one, this is a polynomial function. There's no jumps, holes, or skips, so this is continuous for all real numbers. Another way I know that is there's no square roots, there's no fractions. You just have a polynomial. All polynomials are always continuous. Okay, now let's look at this one. Ooh, I do have a fraction. Well, we talked about way back about the domain. Remember, you cannot divide by 0. That would give you an asymptote or possibly a hole in the graph. Well, let's see. So I know that 2x squared plus 1 cannot be 0. Well, is that ever going to be 0? Are there any values I could plug in for x, square them, multiply 2, and add 1 and get 0? No. So this is always positive, no matter what x is. So that means this fraction, again, there's not going to be any asymptotes or anything. So again, this would be continuous for all reals. Right? Let's look at this one. Okay, we have another fraction. So we look at the denominator. because it can't be 0. We can't divide by 0. Well, if I solve for x, this tells me that x cannot be 1/3. Now, what is happening at 1/3 is really that it's called an asymptote. You should have studied those in college algebra, or get out a graphing calculator and you could see that, although you won't have one on the test. Right? So this would be continuous for all reals except x is equal to 1/3. I mean, everything except 1/3 is it continuous. Right? Next example, same thing. We have a fraction, so we're going to set the fraction, the bottom, the denominator, not equal to 0. I'm going to need to factor that, solve for x, and again, this would be continuous for all reals except x equaling to -2 and -3. These are the values that x is not defined at. Again, those would be asymptotes. Okay, now let's look at this piecewise function. And if you go back to the graphs, you will notice that those were pieces. And usually pieces, unless those pieces are joined, are discontinuous. So how am I going to know? Well, this part is continuous. If I just had y equals to x, that's a line. So that's continuous. And that's another line. The only place where they could possibly be discontinuous is at x is equal to 1. So I'm going to say, all right, well, if I label this as the first part and the second part, and I look at the first part and I go, okay, if I substitute in 1 for x, I get 1. Right? So that means if I have an xy coordinate, that would be 1, 1. But if I look at the second part of the function and I plug in 1, I also get 1. So that means these 2 points are the same, and so those would connect and it would not be discontinuous. So again, these would be continuous for all reals. Let me say this again. If you have a piecewise function, the only place, unless it's a really weird one, which I'm not going to give you, all right, you just need to check out these values. Just plug them into each piece, and if each piece yields the same number, then it's not discontinuous. It would be continuous. If those values would be different, then it would be discontinuous at that x value. Alright, now this one says determine all the values of x at which the function is discontinuous. It's the same thing, just kind of different directions. Right, so same type thing. We're going to look at the denominator. You could either factor that or just solve. Just don't forget to take, when you take the square root, don't forget that plus or minus sign. So this would be discontinuous at x is equal to plus or minus 3. In other words, it would be continuous everywhere except for plus or minus 3. Alright, same thing here. Again, I'm going to factor that, and so it's discontinuous at x is 2 or 1. I would encourage you to pick up a graphing calculator, see what these look like, so you can kind of get the idea, and it should match up to some of the pictures that were already given to you. But you do need to be able to do the algebra on the test. Alright, so just to kind of conclude, continuous just means that if you drew the picture, you wouldn't pick up your pen or pencil, all right? And when you're talking about one-sided limits, we have from the right and from the left, but in order for the limit to exist, that right and left must match. And if they don't, then the limit does not exist.